Hi. Hello. Good morning. Now we are going to see a lecture based on a professional electric. Since I think you guys have adopted this electronic packaging, which is a professional subject related with packaging, since all our electronic students they should explore how a system packaging is going to happen, and also a device package is going to happen. And all these are related with semiconductor packaging also. So we enter into this introductory lecture. This introductory lecture is based on microsystems and micro technologies, and these technologies are going to happen, or it is happening in this era. Once a device has been fabricated, maybe you can take a VLSI chip, or you can take any IC. It may be a digital or it may be an analog. And how these chips are to be packed. The first concern, how it is going to be protected from the electronic interference and from the external environment. So we need to think about in such a way how system packaging is going to happen, how MEMS packaging is going to happen, and also all the semiconductor devices, how it is packed in a perfect way whereby it is suitable for all the electrical signals to pick up and all the sensors, how it is going to be packed and it is stable to the mechanical counter effects, mechanical stability, how it is going to be established. So this introductory will give you an idea why we need packaging. So it's a very simple concept. So many of you wonder like why we need to do these packaging. So what is the effect of this? Just like that we can cover and outer covering alone it can happen in a particular design. But that is not the apt. Here we need to explore a lot what type of materials we are suitably adopting. That is also a very important concern. So let me start. So the books which we need to refer, it is The Fundamentals of Microsystem by Rao Kumala. So that book will give you a lot of ideas how to go with the packaging and all these handouts. Everything has been given earlier and now we go for the concept. So all these are some of the instructions which you need to follow. And now coming to a descriptive part related with microsystems. So first, tell me how a miniaturized system is going to be integrated. So this miniaturization concept is going to be very well understood when we go with integrating a sensor and actuator on the microelectronic design, so which can operate either at the micro scale or at the nano scale of your design. It's going to detect the process and it's going to respond to the input stimuli and thereby it is going to fetch an output stimuli. So output is going to be extracted out of your microsystem design. So the key components which are used is going to be a sensor. So we know what is the description between a microsensor and microactivator. Microsensor is going to detect some parameters, maybe a pressure sensor. It's going to detect a pressure, then a temperature, light, etc. A lot of parameters which you can analyze. And if it's going to be an activator, particularly, actuator is going to have some movement. Say for example, micro pumps, micro valves. So all these can be taken as an example. And everywhere we can just have the word micro. So what it signifies, it's going to be the size. In terms of MEMS, it's going to be micro. And if it is going to be in terms of NEMS, it's going to be nano. So you know the scaling of 10 power minus 6, 10 power minus 9. And if it's going to be with a microelectronic component, then signal processing options are going to be very prominent. And it's going to be with a microstructure, tiny gears, beams, or it can be with a membranes. And particularly when you speak about membranes, it can be a cantilever beam or a cantilever membrane. where all these very much suitable for microfluidic kind of applications. And also in healthcare, we can also see a drug delivery patch, a system. It is one by means of this microstructure design. And packaging, at last it comes. Why it comes at last? The key part is all these are to be designed earlier, it has to be validated. Once your functionality is going to work properly, then we can go for protection and we can establish the interface. So that is the technology here. Microelectronics, mechanics, optics, fluidics, and science. And in class we have a biomems concept also. I think you can just go over the diagram where it is going to have a multidisciplinary aspect, and how the system is going to work. It depends on the microsensor, onboarding part, and also through the actions which are going to be performed, and thereby it's going to have some external communication, how it is established. And coming to the applications of microsystems, atomic, sorry, automotive parts, consumer electronics, medical, industrial, aerospace. These are the main applications where it has to be focused. And coming to the miniaturization, high level of integration is going to be the complex task, enhanced intelligence with respect to the automation, and challenges which are faced. Some micro scale fabrication, so complexity definitely it increases, and ensuring a long term reliability, efficient packaging, and balancing the cost as well as the performance of your particular design. So micro scale sensors and actuators are going to be the components, applications, benefits, challenges, and lot of future trends also we have. So here it's going to be the building block of design which requires some fundamental concepts, not only with microelectronics but also with the photonics, MEMS, RF and wireless communication designs. For these functions to be integrated into systems, they have to be designed, fabricated, tested, tooled, and reliability has to be assured. In other words, they have to be system packaged. Say if it's going to be system package, how the unit is going to look, and microelectronics. So there should be a clear-cut distinction or a difference between microsystems and microelectronics. The field of electronics, which deals with the design and fabrication of so very small devices, it can be such as microprocessor, and lot of techniques are involved with the lithography followed by etching, another fabrication, monolithic IC fabrication design techniques also. So these designs are going to be fabricated with a MEMS or a micro electromechanical system where the structures are going to be very small and thereby it is going to be integrated into the electronic circuits. So imagine a system without a computer. Now all these are going to be the day-to-day updates which you have. Without these, now the survival is very, very difficult. So this everyone can accept, right? So microsystems will have an impact in many areas of your life. It can be voice controlled computers. Now you can see this voice controlled AC which is coming in, right? Electronic notepads, work surfaces, electronic newspapers, flat panel displays. Also, you can have this folded, rolled type of displays which you have on your mobile phones, in which you can see in your laptops, or it can be with your iPads, right? And these are going to be implemented in a micro scale and micro medical implants also, which are very crucial for human life, and watches, the wrist watch also. Nowadays, it's going to have updates, and it's going to be a live update of your human physiological features. So all these integration onto a very small scale into a particular device where it's going to be a wearable device in case of healthcare. So the technologies behind all these and millions of other electronic products. So whatever you take with automotive application, consumer or space, whatever it is in industry, now industry 4.0 and 4.5.0 also emerged. So all these are based on micro devices and the packaging technologies which are involved with human life with respect to these potential. So now look into this particular diagram which will give you an exposure to how this IC assembly process will be carried out. So this electronic packaging is going to have different levels. What we call it is levels here. See hierarchy. So this hierarchy, silicon. So silicon or germanium in the form of a wafer, and into the wafer you can see the small dice. So all are equal space, equal dimension which you can have apart from the corners where you get. So there may be some flaws. And after that, this silicon wafer, it has to be taken to a IC design process. Each die is utilized for this activity, and integrated circuit is going to be fabricated. So this is a well-known process either by a monolithic IC process. We can go over the steps where it is started from silicon wafer, and onto the wafer you have an oxidation, you have a deposition, diffusion, ion implantation, doping. So all these processes are going to be carried out along with the lithography, masking, etching. At last we have the patterning where where these package leads are going to be inserted. So it's a metal lead, which is the outer projection which you have where the connectivity, the external components it can be made. So this is going to be an IC. So before packing an IC, it would be a discrete component where you can't handle it safe. Once it is packed, so you need a packaging unit, that is a final enclosure where environmental stability is going to be accomplished, and also the IC counterparts, what you have at the internal interface, it is going to be protected, thereby the performance of the IC is going to be good. And the next level, so this we call it the level 1. Coming to the next level, multi-chip modules are going to be packed. Once these multi-chip modules have been packed, then we can enter into the level 3, which is a PCB board. Onto the board, now all your discrete elements have been laid. It may be a sensor, a display unit, or it's an interface board, whatever it is, you need to design. So this is a PCB board which comes under the hierarchical level of 3. And from the 3, we can move on to level 4, where you have this motherboards in your PC and how it is getting integrated, stacked, and then connectivity is going to be established. So an entire system has been. So this system is going to be your level. So all these are going to be happening. So level 0 is going to be with the silicon. The way for preparation, all those modules will come. And from level 0 to level 5, this is going to be the chain which is interlinked. Without level 0, level 1 cannot happen. The same thing, without level 1, level 2 cannot happen. So this is going to be the circular chain which you can. So how a system is going to be there. So this entire system is going to have an interconnection with respect to the ICL assemblies and all these micro technologies, micro electrical systems, or it may be with micro electronics. So now we have built a system. We have assumed that we have built a system. This is going to be a very primitive part of the packaging unit. At each and every stage, we have a packing unit where this packing unit is going to be substantial with all the other effects which are going to happen. Now coming to the IC packaging, and it can be with an advanced packaging unit, or it can be with a MEMS fabrication, it can be with an ASIC, application specific integrated circuit, and for the healthcare we can also have sensors and actuators which are linked with a human. Now look into this advanced packaging unit. The key elements of packaged module, it looks like this. A printed circuit board, and you can see these walls which are nothing, it's a connectivity established, and this is a package substrate onto which you can have a IC, you can have one MEMS design, and all these are going to be flip chip packaged. That is advanced packaging technology. Now look into this where hybrid module is also possible. We have a PCB board, and then we have this ball grids, which is going to have the establishment connection where it is between the packaging substrate and the printed circuit board. Packaging substrate is nothing. It's going to be either with a semiconductor silicon, or it can be with a variety of polymers you can have, or it can be the compounds of silicon also. You can have the substrate. And on top you have this MEMS unit, then you have this IC. Now a wire bonding technique is suitable here, where from the substrate and towards your IC. So you can see the connectivity. Why you need this connectivity? So this connectivity is nothing. It's going to have or carry out the electrical signal as input, and it's going to have or fetch your output. So that is the wire bonding feature. Ball grid. It's going to be the ball kind of arrangement which you can have a connectivity here. Here also it's a signal connectivity part. This is by means of a wire, and this is by means of a small dot where the connectivity, a metal dot. Connectivity is going to be established. Metals are very good conductors of electricity. So electrical signal conductivity is going to happen. So IC packaging can be a MEMS packaging unit or an ASIC unit. ASIC is going to have more functionality. So you should differentiate what is FPGA and ASIC. Then only we can go for this. ASIC is nothing, it's an application specific. But FPGA is a reprogrammable feature. All these ASIC ICs are going to be packed. So here you can see these thin wires, it's like a rod or a lead where external connectivity is established. So all these happen only in the packaging. So it's a pure electronic packaging which is going to, and MEMS sensors and activators, they ought to be packed in a similar way. Consumer and medical applications, if you take the packaging market, here electronic packaging with a material outlet, plastic, metal and glass. Glass is also a suitable material for packaging, and there are some regional outlook where in which part of the country we have all this packing, and end use is going to be with consumer, automotive, aerospace, healthcare. So all these will give you a scenario for medical electronics and also with electronic packaging goods. And now we come to the ceramic unit. So this ceramic is going to be a very good substrate material. So where you can see this BGA. BGA stands for the ball grid array. So this is the latest part where it is accompanied with a heat sink. You have a die, a laminate is there, and then adhesives are there to complete the entire conductivity part, and heat sink is going to be uploaded on top. So this is the latest technique which is involved here. So we will continue in the next lecture. I think the exploration with respect to the introduction is very clear. Why we need packaging. So that is a concept which we have seen today. So thank you. We will meet in the next.